How's it going, everyone? Mr. Geyser here with the second video in our Lesson 11 series, where we've taken a look at example 3 and 4, where we'll be analyzing these logarithmic functions. In example 3, we want to sketch the graph of the parent function of f of x, which equals log base 2 of x. First, let's complete that table below, where really all we're doing is we're plugging in that value of 1, 2, 4, and 8 into our parent function for f of x. We get those points of 1, 0, 2, 1, 4, 2, 8, 3. We're then able to plot them onto our graph here and then make that f of graph function on our grid. Now in part B, how is the graph g of x, which is equal to negative log base 2 of x, translated from f of x? What we want to take a look at here is that g of x reflects about the x-axis from f of x because the log function is negative. That a value in front of our log here is less than 0. So if we know that we're going to have a reflection about this x-axis, we should kind of predict this graph here to flip about this y equals 0 line, that x-axis. But I want to take a look at C real quick. We're going to make the table of values for g of x, and we want to graph g of x on the grid above. What we can do is we can actually make a rule for g of x, where for f of x, our x and y coordinate is just x and y, and since we know that all of our values are going to be flipped about the x-axis, really g of x is just x comma negative y. So when we fill out this xy table, we end up using the same numbers, 1, 2, 4, and 8, and we end up getting 0, -1, -2, and -3. We end up flipping about that x-axis where our function becomes negative. We can plot these on here, and we end up getting this blue graph here where it's starting from this positive infinity and going down to negative infinity over here. We can now take a look at D. We want to analyze both f of x and g of x and describe their domain, their range, if they're increasing, they're decreasing, their concavity, their interceptions, and their asymptotes. Let's take a look at f function here. For the function of f, we can see that the domain follows that general form of 0 to positive infinity and the range of negative infinity to positive infinity. Where the function is increasing, the f of x function is increasing, going up at a decreasing rate. The rate of change is decreasing. We'll look further into that later on. We can say that the f of x function is concave down and that 1, 0 is our intercept function and our vertical asymptote is equal to x equals 0. Now let's take a look at g of x. I want you to spot the differences between the two. Ready? Notice how g of x, their domain and range between f of x are exactly the same. F of x here, domain and range the same. G of x here, domain and range the same. But for g of x, it's decreasing. It's going down at an increasing rate. These happen to flip between f of x and g of x. The concavity is now up instead of it being down, which is really easy to see. Our f of x here is facing downwards while our g of x is facing upwards. Our x-intercept is still the same, and our vertical asymptote is still the same. I want to go a little more in depth in that decreasing and increasing rate. If we take a look here at our f of x function, I want you to imagine these lightning lines here as different rates of change about our f of x. Our first rate of change here starts between these two graphs, and we can see that since the graph is increasing, but the rate of change, these slopes between these two different points, is going down as we increase. It's always going to be increasing. These slopes here will always be positive, but it's going to become less and less positive. It's that less and less part there that we're describing when we're saying it's increasing, the graph is going up, at a decreasing rate. The rate of change for this graph is decreasing. However, the exact opposite is true when we reflect it about the x-axis. When we take this g of x here, notice how we're decreasing. The graph is going down, but the rate of change starts off as a very large negative. Then it's a less negative number, then a less negative number. It is increasing over time. However, the slope will always be decreasing, but it's decreasing where it's increasing its slope. It's going from -5 to -4 to -3. Even though it's still negative, it's increasing. So it's going up that negative route, okay? If we were to put these together here on the same graph, we can kind of see how these are both meeting towards the middle here, but our g of x will always be decreasing with an increasing rate, and our f of x will always be increasing at a decreasing rate. It's one of the patterns we'll start to notice with log functions here. However, let's take a look at example 4. For example 4 here, we have 4 parts we want to try and take a look at where we want to try and describe these end behaviors, where we want to get, or if we're given a function, we want to determine the asymptotes and the end behavior while we use limit notation. For part A here, what we really want to take a look at here is just what's inside of that parenthesis. We have that -1 affecting our x, and we're still following those transformation, those manipulation rules, where this is going to cause a horizontal shift of 1 unit to the right. So it's really shifting our domain from that 0, infinity to that 1, infinity. This is going to shift our vertical asymptote to equal 1. Our x equals 1 for our asymptote there. So when we describe our end behavior, we need to keep that in mind. Whereas the limit of x approaching 1, the end of our domain, the vertical asymptote, from the positive direction, our y of x, or our y, is equaling -infinity. We really just need to keep in the back of our heads that general log function, where we have some function that goes along our xy axis, and it goes up and to the right like this. If we're moving 1 unit to the right, everything, the domain and the vertical asymptote, move with the log function. Let's explore this with B here, where in B we're doing 2 things. Where we have one of a vertical, or one at a horizontal reflection about the, a vertical reflection about the y-axis, and we have a horizontal shift. We can see this a little cleaner if we pulled a -1 from both of these terms inside the parentheses to get log -1 of x minus 2. So we pull that -1 out of both of them. We can see that since we have a negative here, we have that reflection about the y-axis, and since we have a -2, it's going to be a horizontal shift 2 units to the right. So what causes, or what happens, is our domain, since it's reflected first and then shift, is from -infinity to +2, where that vertical asymptote is at y equals 2. So now for our left end behavior, our limit of x approaching -infinity now is where y approaches infinity. But as our limit for x approaches 2, from the negative side, y approaches -infinity. That's where it's going down now towards that vertical asymptote. Let's take a look at part C. For part C here, we want to try and describe 3 key characteristics. First, in green, we have that negative directly in front of our log. That's going to cause a reflection about the x-axis. If it's inside the parenthesis, right up here, it's going to cause a reflection about the y-axis. Happens outside about our log, causes it about the x-axis. In blue here, we already know since it's affecting our x, it's going to cause a horizontal shift of 3 units to the left this time. And in red, we end up getting a vertical shift of 2 units up. And I want to try and showcase this 2 units up by kind of restating the function here. I'm going to use the associative property to move that term of 2 onto the other side of log there, where these are the same thing. We just get negative log of x plus 4 plus 2. It's a bit easier to see how that plus 2 is causing that vertical shift then. So let's get rid of that real quick. Really, we just have that domain of -4, because we shifted to the left 4 units, all the way up to +infinity. And we still have that vertical asymptote of x equaling -4, the back end of this domain. We can describe the limit notation similar to how we did in A, where the limit of x approaching -4 from the positive direction is where y equals -infinity. And while the limit of x approaches +infinity, y equals +infinity. Finally, let's put this all together by just looking at C, or by D here. Notice how D just has a vertical translation of 3 units down. even though we're shifting the graph up or down some amount of units, in this case 3, it's not going to affect our domain. Our domain just stays the same, from 0 to positive infinity. Our range actually just stays the same, from negative infinity to positive infinity. Our vertical asymptote stays the same. It's still at x equals 0. And our limits happen to stay the same in general with comparison to that base log of log base b of x, where the limit of x approaching 0 from the positive direction, y would equal negative infinity. And as the limit of x approaches positive infinity, y also approaches positive infinity. Thank you very much for joining me on this second video where we described the end behavior, that limit notation for these graphs, and we explored those two graphs with their rate of change, their concavity, their increasing and decreasing, their domain and range. Thank you very much for joining me, and I look forward to seeing you guys in that next video. Take care.